These are probability notes 9, binomial probabilities. Today we'll talk about what a binomial experiment is. We'll also talk about how to find probabilities using binomial settings. First of all, the term binomial, you notice the prefix bi, which means two. A binomial experiment is a situation where we have repeated situations called trials, and each of these trials has two possible outcomes. We usually call these outcomes success or failure. Think of a problem where you're recording an answer and there are two check boxes. Either this thing happens or the other thing happens. Now you're talking about a binomial experiment. There are three other characteristics that are involved as well. Each of the trials is independent, which means the outcome of one trial has no effect on what happens on the next trial. Each trial has the same probability of success, and the experiment has a fixed number of trials, which means before we start the experiment, we know exactly how many times we're going to run the experiment. There are three situations, A, B, and C, which are experiments that are not binomial. I'd like you to read each one of these experiments and write down quickly why you think each of these is not binomial. Pause the video and we'll see what you come up with in just a moment. In the first example, letter A, we draw three cards from a deck of cards with replacement. When we record the suit of the card, there are four possible outcomes, not two. In a binomial experiment, there are two possible outcomes. Usually we call it success or failure. Now, if you recorded the suit of the card and it was either red or black, that would be binomial. In this case, it's not because there's four possible outcomes. In letter B, you hit a bullseye 30% of the time and you throw darts until you hit the bullseye for the first time. Here, I don't know how many times I'm going to have to throw the darts until I get a bullseye. So we don't have a fixed number of trials. In letter C, we have 30 names in a hat. 10 of those 30 names are names of your friends. 4 names are drawn. Success is having a friend's name be drawn. Here, trials are not independent. We don't have replacement, so that means if we draw your friend's name as one of the first people out of these 30, and there's 4 names to be drawn, so we draw your friend's name, that reduces the number of friends that you have, and it changes the probability. So trials are not independent. If you draw a friend with the first name, you're less likely to draw them with the second name. So what happens on one trial does have an effect. It also changes the probability. So you could use either argument 3 or 4 on that example. Let's take a look at our next example. There's a 25% chance of getting a multiple choice question on a test correct if each question has 4 possible choices, A, B, C, and D, for example. On a 4-question multiple choice test, let's find the probability of getting exactly 2 questions right. Assume independence between answers. For the first bullet, we're going to list the ways that you could get exactly 2 questions right, and one of these I noted as RWWR. You got the first question right, the second question wrong, the third question wrong, and the fourth question right. What I'd like you to do is I'd like you to come up with every single possible way where you could get exactly 2 questions right. So you're going to be rearranging where these R's go. List all the ones that you can possibly think of. We'll come back and see if you got them all in just a moment. So altogether, I came up with 6 different ways that you could get exactly 2 questions right. Now let's move on to the second part. Find the probability of each of these scenarios happening. Now what we've done in this illustration is we've already calculated the probability for this event. For RWWR, getting a right answer, there's a 25% chance. That means there's a 75% chance of getting a wrong answer. So for R, I do 0.25. For W, I put 0.75. And I do that basically for each of these values here. Because we have independent events, we multiply to find the probability of getting a question right and wrong and wrong and right. So we multiply these 4 probabilities together and we get 0.03515,625. What I'd like you to do is I'd like you to go through each of these other 5 scenarios and determine what the overall probability is of each of these events. Write these values down. We'll see what you came up with in just a moment. So I've taken the next 3 possible trial results here, RWRW, RRWW, and WRRW, and I've multiplied 0.25, 0.75, 0.25, 0.75, and I got 0.03515,625. I did that for RRWW, same idea, 0.25, 0.25, 0.75, 0.75, same result. For WRRW, 0.75, 0.25, 0.25, 0.75, same result. You'll notice in each of these situations we're multiplying the four numbers, albeit in a different order, so we should always get the same results. So obviously for these other two possibilities, we're going to get 0.03515,625. The last step we're going to do at the bottom bullet is we're going to add these values together. Go ahead, pause the video, do that. Let's see what we get, and then we'll move on. So when you add these values together, you should get 0.2109375, and that is the probability of actually getting 2 questions right on a 4-question test. Now, there is a shortcut because this took a little while to do, and the shortcut for doing a binomial experiment with n trials, having a probability of success p in each trial and a probability of failure q, can be found by using this formula. The probability of k successes equals npk, so this is a permutation, times the probability of success to the k power times the probability of failure to the n minus k power. So what we're going to be doing here in this problem is we're going to be substituting 0.25 for our probability, 4 for the number of possible choices, that's n, and 2 for k, which is your success. Just a quick note, this is NPK. This is not a probability, this is a permutation. It's kind of like the NPR notation we had last unit. So what we're going to do is we're going to substitute the values into this little problem here. 4 again is your n value, that's going to go in here. So this is 4p. 2 is your number of successes, that's going to go here for k. Then it's going to be p, the probability of success, 0.25 to the k power, we already said k was 2. And q is the probability of failure, which is also 1 minus p, so the probability of failure we said was 0.75. And n minus k is 4 minus 2. It's what you get when you subtract the numbers before and after this p for permutations here. And 4 minus 2 is 2. So this 2 actually represents the number of problems you get wrong, and this is the number of problems you get right. You can use your calculator and crunch this out. Let's see what you come up with, and we'll talk about your answer in just a moment. When you crunch this out and you want to do this all at once on your calculator, don't break it up, just type it in directly as you see it. Remember, on your calculator you can generate this value by doing 4, finding the NPR command, and then hitting the number 2. If you crunch all this out here, what you end up with is 0.2109375. What do the numbers in the formula represent? If you actually crunched out 4p2, this is equal to 6. This is the number of different ways of writing our possible ways of getting 2 problems right. 0.25 to the second power means we multiply 0.25 twice and 0.75 twice, which is what we actually did up here. In each of these problems we did 0.25 multiplied twice, 0.75 multiplied twice, and we did this 6 times altogether. So the numbers in the formula basically are a shortcut for what we did earlier. I'd like you to use a formula to find the probability of getting exactly each of these number of questions correct. For example, if it was 0 questions right, you would have something like 4p0, 0.25 to the 0 power, and 0.75 to the 4th power, because n minus k is 4, and you'd multiply these values together. Figure out this one, solve the other ones out. We'll see your answers in just a moment. So the different values we got for getting 0 questions right, the probability is 0.3164 approximately. For getting 1 question right, about 0.42. That's the most likely scenario. 3 questions right, there's only a probability of 0.046875. That's about a 5% chance. And the likelihood of actually getting all 4 questions right is less than 1%. What we're going to do finally is we're going to make a probability distribution and graph this based on our results. We've already come up with the different possible scenarios when getting number of questions right out of 4 questions. So what we're going to do in our chart here is I'm going to write down for x the number of questions that we could possibly get right on this test. And in the box underneath we're going to write down the probabilities, so now we have everything in order. So I'd like you to copy down these probabilities, put that in the p of x row right here, and then I'd like you to graph this probability distribution on the histogram. We'll wrap up and take a look at your answer in just a moment. So we've inputted our probabilities into the probability row, and again you can see the most likely 2 or 3 scenarios you have when answering a 4-question, 4-choice, multiple choice test are 0, 1, and 2. It's pretty unlikely you'll get 3 and 4. It's a lot of times easier to see this though based on a graph. So what we're going to do is for each of these probabilities we are going to graph a bar that represents the probability for each of these events. So you can see at 0 we have a pretty tall bar. Whoops. Our tallest bar though should be at 1, which goes up to about 42%. Our bar at 2 should go up to about 21%. Our bar at 3 should only go up to about 4%, so that's between 0 and 10%. That's way down here. And the probability of 4 is barely you're hardly going to see much of anything at all here. Now when you don't have an electronic pen, hopefully you'll have a little bit better picture than what I had, but that's kind of the idea of your probability distribution. And that wraps up your notes for today.